All right, so here is part 2 of the Solving Quadratics video series. I do want to look back on example 4 that we solved by using difference of squares and by factoring, and showing you that you can use what's called the square root property. What you would do in that case is you would have x squared minus 9 equals 0. And because our bx term is a 0, you can move 9 to this other side. One thing that you need to be very careful of, though, is the inverse operation of squaring is a square root, but both negative 3 times negative 3 get you a positive 9. And positive 3 times positive 3 get you a positive 9. So when we take the square root of both sides, you must consider both the positive and negative square root of the right-hand side. And notice that gets you the same answer as up here. The last set of examples are going to be solved by what's called the quadratic formula. It is important that you understand this formula can be used for any quadratic, but it is specifically useful when you cannot find two linear factors. For example, in number 5, if I needed to find two numbers that multiply to positive 1, but then add to 5, I would not be able to find two integers that do so. So our quadratic formula allows for us to solve for those zeros and find the two zeros that would be able to solve our quadratic equation. I say x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Let's simplify inside the radical. I would have the square root of 25 minus 4 all over 2, which gives me the square root of 21 over 2. Now, the square root of 21 is not a perfect square, and it doesn't even have two factors that are perfect squares. So I'm going to just say that x must be equal to the addition and the subtraction as two separate zeros. And this is why we could not solve this using factoring, because this is not going to be integer numbers. These are going to be real numbers. They're going to be rational numbers, but they are not, or they're going to be irrational numbers, but they are real numbers. All right, let's look here. Now, again, I would want to look at this, and I notice a 3 and 15, and just like the example we did in the previous video, we might want to look at it and be like, can I factor a 3 out of everything? But I can't factor a 3 out of negative 10, so I am just going to plug this into the quadratic formula. So I have negative b, changing that to a positive 10, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. All right, let's work inside that radical piece and make sure that we simplify. So 10 plus or minus the square root of 100 minus 4 times 3 gives me 12 times 15 gives me 180 all over 6. When I simplify inside that radical, I get the square root of negative 80. And let's think about how I might be able to simplify negative 80 and find some perfect squares. I know that 80 is 4 times 20, and 20 is 4 times 5. Therefore, I could rewrite this inside piece as negative 1 times 4 squared times 5. The square root of negative 1 means that this is going to be an imaginary number. The square root of 4 squared means I can take 1 4 on the outside and leave just the square root of 5 on the inside piece. Now all of my numbers in the top are even and the denominator is also even. So I could simplify by dividing each and every term by 2 to get this as my answer. Just like we wrote before, you could then write both the positive and the negative as 2 separate zeros. Notice that my 2 solutions in this case are complex numbers. We'll talk a little bit more later when we talk about graphing quadratics, why it's going to be the case. But notice we don't have any real roots. We have complex roots. You can look at just the discriminant, which is the inside of your square root, to determine how many solutions your quadratic is going to have. If the inside piece ends up being 0, for example, if you end up getting 4 plus or minus the square root of 0 over 2, let's just say, then you are only going to have one solution, and that's going to have a multiplicity of 2, meaning this root happens twice, or when you do find your 2 factors for whatever, and I just made up this equation. If you're like, where did she get that? I just made this up to go off of this example. When you have your 2 factors, you'll notice it's the same linear term twice. If the inside is positive and a perfect square, then you're going to have 2 nice, pretty rational solutions. If it's positive and not a perfect square, like when we had the square root of 21, then we have 2 decimals that can't be written as fraction solutions. And if you end up having a negative on the inside, you would have complex solutions.